Hello, friends. I'm Dr. Vijay Prakash, and today I'll be speaking to you about a very interesting topic that is 4D printing, future to smart prosthodontics. So, if we see the practice of prosthodontics, these are very common treatment modalities which we see the complete dentures or the partial dentures. Now, if we look at these materials, they are static material, and these static materials are made up of a rigid material, and these are basically placed in a dynamic environment. Like if we see the slippery bases, like the mucosal tissues, the ridges in relation to the teeth, so you have a static rigid material which is supposed to function in a dynamic environment. Suppose we have a material which can reorient, reorganize, and readapt according to the simulation, according to the environment in the oral cavity, according to the force requirement in the cavity. That will not only improve the retention but also the stability and the longevity, patient acceptance. This all will be very nice in this type of material. So I'm talking about the future technique which will be, and that will be possible only through 4D printing. Now, if we see, we 3D printing in routine prosthodontic practice is becoming very common these days. 3D printing or additive manufacturing, it allows researchers to create complex shapes which was previously impossible using traditional fabrication methods, as we know. So it started with Charles W. Hull in 1986, who first introduced the concept of three-dimensional printing, and later this was called as additive manufacturing or rapid prototyping. Now, if we see the conventional three-dimensional printing, it describes a technique which creates a 3D model by adding the material layer by layer. And this material can be ceramic or a metal or a plastic or a polymer. So the common 3D printing technologies which we commonly use are the material extrusion, wet polymerization process, fused deposition modeling, inkjet printing, laser printing, and stereolithography. Now, if you see the conventional 3D printing technology, which we commonly encounter in a routine practice, it is basically fabricating a static structure, and that also from a single material which cannot meet all the demands of the dynamic function which is needed for application in dentistry. So that is the reason when I introduced the topic, I was talking about dentures, which were static materials. They can also be 3D printed through CAD/CAM dentures, but that will all be static and a rigid material. So recently, a focus has shifted from a three-dimensional printing to four-dimensional printing, with the aim of providing restorative material which can dynamically alter shape under the influence of external stimulus. And this approach would be very useful if you talk about regeneration, rejuvenation of the material, restoration or replacement of defective restorations, even replacement or healing of injured functional living organs and tissues. That can also be possible through 4D bioprinting. So, who started 4D printing? It was started by Skylar Tibbets and his co workers in 2013 uh, when they were working in a self assembly lab in MIT, USA, who has designed a self folding structure that reshape over time under certain environmental conditions. So they converted the stable 3D printing materials into actively moving objects by the novel 4D printing approach. Like you can see in the figure also, if we see this stable material, now with the stimulus, this can open up and self-fold into a different shape. So it was a different shape initially, and it becomes a different shape eventually because of the programming of that material. Now, what do you mean by four dimensional? You have all these dimensions. 1D means a single line diagram. 2 dimension means an area. When we talk about an area, length into breadth, that is an area that is known as the 2 dimensional. 3 dimensional is when we involve height, or we talk about the volume of a structure, that forms 3 dimensional. As you see in a routine 3D printing techniques, you have a 3D model. So those are 3 dimensional. Now, 4 dimensional, fourth dimensional here is basically time. So when we consider, apart from the volume of a structure, we also consider that with time it changes. We call that as fourth dimension. So it results in a self-folding structure on when we subject that to a stimulus or an environment. So you have a self-folding materials is the name given for the outcome of the recently introduced 4D printing technology, and 4D printing is based on addition of the fourth dimension as I just mentioned, and that is motion over time. So the aim of 4D printing is to produce functional objects rather than the static one. Another thing which is very important is self-assembly. Now, what do you mean by self-assembly? It is basically a process by which a disordered parts are used to build ordered structure through only local interaction. So, local interaction means interaction with the local environment. So, if we are talking about, say, a denture, which I gave an example initially, so how does it respond to the environment, that is the oral environment, and how does it respond to that and changes? So you basically have various smart assembly revolution. It all started with digital computation. You have DNA computation, material programmability is there, chemical programmability is there, CAD nano, which is now being used. You have, as I told you, there is a lot of research on bioprinting of the material of tissues and cells. You have nanorobots, which are used in a big way, and you have molecular microorganisms. Now, what is 4D printing? So, by definition, 4D printing is a process through which a three-dimensional printed objects transforms itself into another structure over the influence of external energy input such as the temperature, light, or the other environmental stimuli. So, if we see, you have a 3D printer, you use a smart material rather than a regular material, and it results into a different type of structure with the help of 4D printing, which can self fold and respond to the given environment over the period of time. So 4D printing is a process of self-folding over time under thermal and humidity changes. It could be thermal changes, it could be magnetic changes, electric field changes, etc. So this concept relies on understanding how the microstructure of a 3D printed model can undergo spontaneous shape transformation under thermal or moisture changes. So if we have a flat surface like this, so on relation with the external, on coming in contact with the external stimulus, it could be water, magnetic field, or temperature, as I mentioned, it changes a shape into a different object. So on respond to that. So 4D printing relies on 3D printing of multiple materials, which are followed by selective photo curing to give the 4D printed objects a motility nature, or it shows a kind of motion. So that is the reason a fourth dimension is motion over time. So the transformation mechanism can be assessed by evaluating the strain properties of each component within the printed model and putting them under a controllable pattern. Like, you have to program that material in order to make it smart. Then only it will behave like a smart material, and it will respond to the environmental changes. So 4D printing facilitates precise configuration of the material response with better material adaptability. It is an emerging technology where the greatest advantage lies in its ability to create 3D structures of living things such as tissues, organs, nutrients, and cells. So 4D printing can be widely used in regenerative medicines, material science, chemistry. Now this is all in dentistry. This is all a medical field uses which I am seeing. But 4D printing it will be used in a very big way in the industrial. It is going to revolutionize the industries. So, if we talk about bioprinting only, this technique is rapidly evolving to fabricate biomimetic structures, structures which can mimic the biology of the tissues and which have a great potential for clinical biomedical applications and regenerative medicines and dentistry. So, if we talk about 4D printing in dentistry, if we see 4D printing would have a good impact on different specialities as the technology can produce dynamic and adaptable materials. So, if we talk about prosthodontic practice or conservative practice or even orthodontics, in fact, other parts, other branches of dentistry, in all 4D printing is going to find use. So, undesired, what we basically encounter in a routine dentistry is basically undesired dimensional changes, thermal instability is there, and in prosthodontics, if we see polymerization shrinkage, basically results in the denture not fitting in the patient's mouth, or the restoration which we have done that has a tendency of micro leakage and nano leakage. So all these are problems which can be overcome by the use of 4D printing technology. Now, how does 4D printing work? Now, 4D printing has two essential steps. One is processing, another one is programming. The model is firstly processed into an original shape, then it is programmed to convert to another shape when exposed to a certain stimuli. Say, for example, at a body temperature, it is going to behave differently than it was initially made. So, it basically shows a self-folding pattern. So, the mixing of the microstructure into a controlled measure can be challenging, and the manner in which these materials undergo programmed movement is called programming to convert into a dynamic smart materials, as I mentioned before also. So basically, from a static material, you are converting that into a dynamic smart material. So if we see 4D printing, what all you require a smart material, you require a 3D printer. It will result in a smart static structure. So once you program that material with the stimulus and the environmental conditions, it results into a smart dynamic structure. Now, what are components of 4D printing? One is multi-material 3D printing technology. Second is smart materials, like it could be heat responsive, moisture responsive, photo responsive, or electromagnetic. So these are all the stimulus which we can stimulate the material and make it smart. Mathematical modeling, it could be forward or backward, and interaction mechanism, that is the stimulation programming of that particular material. So you have the simulation software, and this simulation software can be Autodesk, CATIA, or open source. And you have the multi-material printers. So the 3D printer which we use has to print multiple materials at a time. It could be Stratasys, Rova, SolidView, Geomagic. These are some examples which can print smart materials. And smart materials can be shape memory alloys of shape memory polymers, self-healing materials. So these are smart materials. Essentially, if we see the difference between the 3D printing and 4D printing is 3D printing only results into a static structure, but 4D printing, it results not only with the static structure, it converts that into a dynamically intelligent structure. So now the technology, the additive manufacturing technology, if we see based on the mode of material or ink deposition, it can be classified as extrusion based methods and wet polymerization methods. So extrusion based methods are fusion deposition modeling, direct ink writing and inkjet, and wet polymerization are stereolithography and digital light processing. So first, the extrusion based modeling. In this, you have a very common example, that is fusion deposition modeling, FDM. It works on the principle where the filaments are melted in a heated nozzle and forming a 3D object on the base of the printer in a line by line and layer by layer manner. As you can see in the figure also, it forms, you have a melted material which is feeded, and line by line and layer by layer this model is being formed. So materials which are used with this type of printer are polylactic acid, ABS, that is acrylonitrile butadiene styrene, polycarbonate, polycaprolactone, polyethylene terephthalate, and polyphenyl sulfones. The advantage with this technique is it is easy to use, it is low cost, it is having a fast printing technology, the low cost of the equipment and material, and non requirement of any chemicals. But the drawback here is there is resolution of X, Y, and Z axis, which is limited by nozzle dimensions. There is fabrication of complex geometry, and it is having limited accuracy as far as if you talk about the flow rate, the material properties, and heat transfer dynamics. Next technique is the direct ink writing. It is based on the principle of extrusion, which is constructing the microstructure layer by layer by using a computer controlled robot. So here, instead of manually feeding the material, you have a computer controlled robot which moves the dispenser filled with printed ink. So widely used for additive manufacturing and provides excellent interface combination and adjustable mechanical properties. And the materials which are used are metal, polymers, ceramics. And in this technique, viscous liquid ink is deposited, forming a 3D object line by line and layer by layer, as we have seen in the FDM technology. So during extrusion, there is an increase in the shear stress, due to which the viscosity of the ink will reduce gradually and the ink can flow freely. The system can be stabilized using appropriate materials such as the ferric oxide nanoparticles, which helps in stabilization of the material. And recently, if we see the high resolution printer, they achieve high resolution with the help of micro nozzles. Now, essentially, if we see this part B of the figure, you can very well make out what we require. So you have the 4D printing will only take place once you give a stimulus like heat, electric field, light, or magnetic field, and you use a smart material like shape memory polymers, shape memory metals, you have hydrogels, you have liquid crystals. So all these materials, the smart materials, once you use, and then they form a dynamically smart materials which can be used in a dynamic environment. So the advantage with this technique is you have multi-material printing at the same time. Multiple material choice can be made. There is an open source of controlling machines. It does not require drying or solidification process, and it maintains shape as soon as it contacts the substrate. The drawback is it is having high cost of fabrication, the build volume is small, and the viscosity of the ink needs careful regulation. Apart from this, you have a common 3D printer, that is the inkjet. It works on the principle that both a single and a multiple nozzle can be used simultaneously. It uses a non-contact technique utilizing either a thermal, piezoelectric, or electromagnetic forces, which helps in expelling the successive drops of the inks onto the substrate, which replicates the CAD design. And this is also called as drop on demand printers. So different light curable liquid resins can be sprayed, and you can use different approaches like thermal inkjet can be used, or piezoelectric inkjet can be used, and its mechanism of action is by selectively depositing binding materials through a print head in order to fuse a thin layer of powder to a previously fused layer. So this is how it will deposit. The advantages is it is fast and cheap method, wide range of materials can be used, and you have a typical planar resolution which varies between 30 to 40 microns to 200 to 400 microns. The drawback is it lacks precision of drop size and placement. There is a frequent nozzle clogging, so frequently you have to either change the nozzle or clean the nozzle because of this clogging, and you don't have enough storage, and as I told you, it clogs the printer head. So wet polymerization method is another method on which 3D printer work. You have very commonly used stereolithography, which was first developed by the inventor, the Charles Hull, in 1986, and it is currently one of the most widely used rapid prototyping method. It works on a principle that a liquid resin is polymerized and cross-linked into a solidified polymer, which is induced by a light source. And this light source is basically a laser source. It is characterized by high spatial resolution and a high fabrication speed. The source of radiation is the gamma rays, the X rays, electron beams, ultraviolet rays, and it can be visible light. On exposure of light, one layer is completely printed and the building surface will move up, then the next layer. So basically, it pushes and once it build up the one platform, it then pushes that platform lower and then it again prints another one. So this is how layer by layer it is printed. So recently magnetic assisted stereolithography is also developed, which helps in fabrication of a material intelligence for various new applications. That is, it helps in making smart materials. The advantage is it can print parts with complicated geometric shapes. It provides better surface finish. The application here is it is smart material which can print with high shape fixity, and it maintains excellent shape memory. Customized implants in uses like cranioplasties or orbital floor or nasal floor can be used. You can form precise surgical guides for implant placement. Precise and specific fixed processes can be made using stereolithography, and bioprinting of living tissues with smart materials can also be made with this technique. Next is the digital light processing. Now, in this technique, it can cure the entire pattern in a layer by layer in a single exposure. So far, we were talking about line by line and layer by layer technique, but in this digital light processing, the entire pattern in a layer can be cured in a single exposure. So it is an emerging rapid prototyping technology which will be essential part of 4D printing because it can be done rapidly. So this additive manufacturing technique is closest to the production level, and it can achieve high resolution on both the micro and nano scale through optical lens systems. It can be used to print environmental responsive self-folding structures which are based on smart materials like polyethylene glycol dimethacrylate. So adjustment of light can help achieve different degrees of cross-linking, and it can be used in manufacturing multiple layer shape memory objects which are composed of different methacrylate copolymers, which are called as the projection microstereolithography. So compared to conventional method, it has a high print speed. That is the great advantage, and that is the reason this method is one of the closest method for printing for to be used in a 4D printing technology. So this technique can also be used for bioprinting of natural tissues and organs. Another very big advantage which can be used in the coming future. So stimulation of method of 4D printing. Now, as I told you, that the smart material becomes smart once it responds to the stimuli, and those stimuli can be your external stimuli or an internal stimuli. Now, external stimuli can be water, humidity, temperature, light, electric field, and magnetic field, and internal stimuli can be your cell traction forces. Now, stimuli responsive polymers, they can be either one of these stimuli, they can be sensitive to either one of these stimuli, or they can be sensitive to multiple stimuli. Now, they can be physical stimuli, chemical stimuli, and biological stimuli. So, physical stimuli, you have temperature, light, magnetic field, or the electric field. And chemical stimuli is when the material is sensitive to the pH changes, the redox or solvent changes. And biological stimuli is on basis of glucose or enzymatic reaction. So the polymer or whatever material you are using can be sensitive to either one or multiple stimuli. Water humidity. Now, this is based on the theory of swelling and shrinkage, and it is one of the first used stimuli in 4D printing. And if you remember that Scarlett Ibbotts also used this particular stimuli when he first made a self-folding material. So the degree of expansion or contraction of humidity sensitive material should be precisely controlled during transition to maintain the integrity of the printed structure. So you can have, if you see, you can have a material which can be a passive material, another one can be an active material. Now active material means it is sensitive to these stimuli, and the passive material is it is not sensitive to these stimuli. So this is how you can make it happen and make it self-fold, depending, and you will be placing what changes you desire. According to that, you'll be placing the active material in that particular position and program that. So the materials used are cellulosic pulp hydrogel. You have the cellulose with sterile. And the advantages is it is convenient and a clean method. Drawback is it is having slow response. Next is temperature. Now it is one of the most commonly used shape shifting stimuli, and it is based on internal stress inequality. So the very common materials which are used and which make use of temperature or thermal changes are shape memory polymers, which are used and they are sensitive to the temperature changes. Like for example, if you see this material which is flat on 25 degrees centigrade, but as you increase the temperature, the shape changes and forms into a different type of a material. And also fiberglass glass polymers can also be used. So the advantage is it is better control, it is adjustable, it depends on the change of temperature in the environment. The drawback is the response is slow and it is complicated. Light. Now, if a material is sensitive to light, it will show changes. So, light is a common indirect stimulus that regulates the polymer shape through remote induction. So, the polymer shape can be altered by using a light trigger with a different wavelength. Like, for example, we commonly use composites. So, composites which are light activated get cured when we show light onto these materials. So they are based on the principle of photothermal effect. It is widely used in the field of 4D printing because of its rich source of energy. It is wireless, secondly. Thirdly, it is having a controllable property. So it depends, if you show light, then only it is going to cure or it is going to achieve its function. Otherwise, it will be in a different shape. So the material used here are alginate and polydopamine. Advantages, it is having a high resolution and it can be remote controlled. And drawback is the use is complicated. Next type of stimuli is the electric field stimuli. Electric field can also be used as a stimuli in remote control. It produces resistive drive to fill the smart polymers with a conductive fillers. It is based on the electrothermal effect, and the material commonly used here are ethanol and silicone elastomers. So advantages with this type of stimuli is it is fast, but the drawback is the operating inconvenience. Next is the magnetic field stimuli. Now, if we see the magnetic field stimuli, it is magnetically induced shape recovery, and it can be achieved by doping smart polymers with a magnetic nanoparticles. So you have to inject these smart materials with magnetic nanoparticles, and if if that smart material is subjected to a magnetic field stimuli, then that is going to respond accordingly. So the shape recovery of a smart polymer can be induced by heating in a alternative magnetic field, as I just mentioned, and it is based on the theory of magnetic field. Advantages can be remote control, drawbacks operating inconvenience. Next is the material system. So far we have talked about the additive manufacturing techniques, we have talked about various types of stimuli, and next is the type of smart materials. So the types of materials which are most widely used in 4D printing are shape memory polymers, shape memory alloys, you have hydrogels which can be programmed after printing. So you have a stimuli response hydrogels, which have a very wide application. Um, you have shape memory polymers. It will have a very important use if we talk about prosthodontic practice. So memory polymers have high stiffness and show rapid response to stimulation, which can produce large recoverable deformation after external stimuli. It consists of two segments. One is it is a highly elastic component, and other one is capable of reducing its stiffness under the certain type of stimuli. So that is how it will make the change, because one side is highly elastic, that is going to bend, but the other side is going to control that stiffness. So with how much of change you want, accordingly you can increase or reduce the quantity of that particular segment, and then you'll get the desired change. So the mechanism is, after a particular stimulus, a switch or transform is triggered, and a strain energy which is stored results in a temporary shape, which releases and results in a shape recovery. So the material which are commonly used are polylactic acid, ABS, that is the acrylonitrile butadiene styrene, and polyvinyl alcohol. Literature shows that most of the material used in 4D printing has a shape memory capabilities. Now, newer multifunctional shape memory polymers or nano smart shape memory polymers are composites which can be used, and shape memory polymers can also have multiple shape memory effect and can have a reversible shape memory which can memorize multiple shapes and reversible shapes. So 4D printing shape memory polymers can not only carry out simple shape changes, but also can realize shape deformation, shape assembly, self assembly, self repair, and other functions by presenting a deformation schemes like target shape, attributes, function. Like, for example, if you see you have done a restoration in a tooth, composite restoration. Once you have cured the restoration, one of the most common problems which you face is micro leakage or nano leakage. Now if you know that there is a micro leakage or nano leakage, so you can program that particular composite that over a period of time that is going to self repair or self assemble, and the gap which was there between the restorative material and the tooth, it's going to be automatically filled with the time. So that is the beauty about the 4D printed material, because you have programmed that material in order to act against the act in response to the stimuli. So types of shape memory polymers. You have shape memory polymers which are of three types. You have thermally induced shape memory polymers which have two incompletely compatible two phases, like the stationary phase which remembers and restores original shape, and other one is the reversible phase which ensures shape changes. Next is the light response shape memory polymers, which can be photosensitive depending on the photochromic chromophores, which restores the original shape and can be accelerated by light of different wavelengths. So when we show light of different wavelength, there will be accordingly different types of changes. So chemical response shape memory polymers can also be there, which have usual method of chemical induction like the pH changes, equilibrium, ion displacement, etc. Next type is the hydrogels. Hydrogels have a good biological affinity and can be reversibly deformed in response to some stimuli. This will have a very wide range of application, and that is the reason hydrogels are very important part of research. So degree of swelling depends on internal properties including cross-linking density, microstructural anisotropy, and hydrophilicity. Advantages: they're highly biocompatible, and that is the reason it is in a big way used in bioprinting of tissues and cells. Easy to print, easy to synthesize, adjustable, high alignment, and low cost. So types of hydrogels can be depending on the response of the environment, that is stimuli, which can be temperature responsive hydrogel, light responsive hydrogel, and pH responsive hydrogel. Temperature responsive hydrogel are basically the volume of gel changes with the temperature changes, and these volume changes are reversible. It can be used in smart sensors and actuators. Light responsive hydrogels, these gels can provide possibility of environmental stimulation based on intensity of light. Gel response either by molecular exchange or through physical or chemical properties such as viscosity, elasticity, shape, or swelling decrease. Now this type of hydrogel can find application when we talk about different types of restorative materials, or where we want to self heal the tissues. Temperature responsive hydrogel can have applications when we talk about a type of processes which can adapt to the temperature changes. Again, pH responsive hydrogels can have applications where there is change in pH, like in the oral environment, where a patient is taking different types of food, so that pH can accordingly alter, and therefore you have a material in the mouth which can adapt to do the changes of the pH. So the volume changes in gel depends on concentration of internal hydrogen ions in response to the change in pH, and it can be used widely in biomedicines. Apart from this, you have assembled all this. These are the components. Next is mathematical modeling, very important, because that is how, on basis of this, you are going to program a material. So first thing, you have to determine what will be the final desired shape, how much of change you require. These stimulus properties, what type of stimulus, or based on that you will require that change. And the material properties, the smart material which we are using, what type of property it is having, how much of stiffness it is having, how much of swelling ratio it is having, how much of glass transition temperature it is having, and the material structure, what type of material structure it is. So accordingly you are going to program that material in order to make it a dynamically smart material. Now, application of 4D printing. Application of 4D printing can be tissue engineering, drug delivery, orthopedics, dentistry, stents, soft robotics, microfluidics. It can have a very, very wide range of application. Like for example, a shoe industry. You in the coming time, you'll be having shoes in the market which can adapt according to the environment. Like for example, those particular shoes will behave differently in a rainy season when you are applying water, so they will become waterproof. And it will be different when you are jogging, it will be different when you are walking. So it will actually adapt according to the environment. It can have applications in defense, rockets, your aeroplanes. It has a very, very wide range. Microfluidics, say for example, pipe systems. You have a pipe which behaves differently in a cold weather. It will shrink, and you have pipe, the water pipe, which will expand in the summer season. So accordingly, it will adapt according to the change of environment. Now, if you talk about prosthodontic applications, the biomechanical properties of restorative dental materials which we require, which we desire, are strength, color stability, adhesion, longevity, and which we have to keep in mind. If all this is not there, then that will result in failure. So the oral environment, in terms of its dynamic nature as well as the functional balancing forces, presents a challenge, because it is so much of a dynamic situation in the oral cavity, so much of changes occurring. So the common factor of failure for restorative material is basically dimensional changes, and we all encounter that there. And one of the very common reason for this dimensional change is, say, polymerization shrinkage, micro leakage. So 4D printing material can basically make continuous self-folding adjustments, and they can be capable of moving towards the periphery and can avoid micro leakage or overhangs of the margins with the use. They can also adapt to the type of pressure, to the type of force which is applied onto the particular processes. So 4D printed material can move only in certain directions as programmed before their production. And adjusting the path of motion of 4D printing material in restorative dentistry can eliminate the use of dental adhesive. Now, if you talk about etching, bonding, that use can be eliminated if you have a self-folding material which is programmed to move towards the tooth structure on actually coming into contact with a certain type of environment. So that will be of great use, because that will eliminate etching, bonding, all this type of things it will eliminate, and you'll have a structure which will be mechanically retained in a in the tooth structure. So 4D printed restorative material can be programmed to move downwards towards the fitting surface of the tooth to ensure maximal adaptation and maximum longevity of that your treatment. In addition, 4D printed fillings can be used for inaccessible areas in the oral cavity where manipulation and longevity of the current restorative materials are difficult to achieve. So 4D printing can be used in removable and fixed prosthodontics. I have already given example of removable prosthodontics. In fixed prosthodontics also, if you have a uh, smart like you have the smart material polymers, accordingly you have the smart ceramics. So if you have a ceramic material which can close down the gap, you will eliminate the problem of micro leakage, and your marginal adaptation would be good, and that will result in success of your treatment. So the technology can produce materials with similar properties of natural hard and soft tissues, and basically that will result in longevity, greater patient acceptance, and um, more successful treatment. So in addition to 4D printing, material can adapt to various types and direction of forces, as I told you, in the oral cavity. So 4D printed prosthetic materials can have reliable fitting and retention characteristics and optimal dynamic properties, which according to their self-folding nature. So the denture base can be fabricated of certain structures that can encompass elasticity, thermal criteria like change whether the patient is having something hot or cold. Accordingly, the processes can change, which can simulate the reaction similar to the periodontal ligament or overlying mucosa. So, in addition to that, you have wide varieties of designing options which can be provided for patients with individual demands. For example, the patient with areas of residual resorption. So, you can have a material which can repair over a period of time. So, the advantage of basically over residual resorption, that can also be compensated by using such type of materials. In implant dentistry, if we see, the folded printing structure can be used as fused to the currently available implant in the apical region. So if you're using an implant in the apical region, and you know that your implant is near the vital structure like the inferior alveolar nerve or mental foramen or your maxillary sinus, so you can have a softer material which can be attached to that, which can be a smart material, and that will help in avoiding injury to the vital structures. So thus this technique can overcome sophisticated surgery such as sinus augmentation or nerve repositioning. And in addition to this, you have stem cells, which can be carried on 4D printed implants or tooth shaped scaffolds to grow into a natural teeth. Of course, that is, we are desiring that will be the future, where you have a patient with a missing space, and instead of placing an implant, you just inject a solution into the empty socket, and after a certain period of time, that will result in a tooth. It will grow into a tooth. So that is definitely the technology which we can encounter in the future. If we talk about temporomandibular joint, again you can have 4D printed cartilages which can adapt to various movements of the joint, it can adapt to various wear of the joint, and continuous, and it can compensate for articulation and occlusion. So 4D printing has a very, very wide application. It relies on sequence and path of movement, which determines the self-folding pattern. So designing of steps should take into account the movement of the circumferential structures around the 4D printed prosthetic appliance. And another important aspect is shaping time under thermal and physical conditions, or if we talk about any type of stimuli like electric field or magnetic field. So the self-folding time cannot be infinite. So there is a limitation to that. That is, the material cannot keep undergoing dynamic changes continuously over a period of time. It will only make changes which it is programmed to do so. And also there will be a limitation to the material which will be used. So there should exist the so-called self-locking property. It should not happen that the material is just changing dynamically, and there is a desire that the material should stop. Once we achieve the desired function, it should stop and self lock itself, which will be capable of controlling folding sequence. That is, application of smart key lock connectors can be useful, and 4D printed structures can mimic properties of body structures, and they should have adequate strength. Definitely the 4D printed structures or processes which can give to the patient should have adequate strength. 4D printed technology can have a very wide application. If we talk about maxillofacial prosthodontics, where we are designing, say, a facial processes, and the problem which we encounter is, one of the problems which we encounter is adhesion of the artificial material with the natural tissues. So if we have a 4D printed smart materials, and which we program that in order to adapt towards the natural tissues, then the problem of adhesion of these maxillofacial processes can be eliminated. So the major capabilities of 4D printing technology is: one, self-assembly; secondly, multifunctionality; thirdly, self-repair and healing. So finally, to conclude, 4D printing can have a significant impact on aspect of dentistry, whether you're talking about any type of any branch of dentistry. Even if in orthodontics, we can have smart memory alloys, in which we adapt that brackets or wires or even different types of orthodontic appliance, and they can self-correct because they are programmed to do that, depending on what type of program you have undertaken to correct that malocclusion. So with further prospective analysis, introduction to smart materials, artificial intelligence, and latest printers, this would be the future to smart prosthodontics. Thank you for watching the video and listening patiently. Thank you.